Zurich, and he will be talking about puzzle boxes.
So it was very nice having Julio's talk just before me, because I'll be able to connect a few things to what he said. While studying a similar topic, or at least there's some overlap with Julio's work, we came from a completely different direction. We actually came from cryptography and the importance of this kind of non-causal systems for cryptography. So just a very general statement of the kind of things we try to say in cryptography. For example, we want to say that no adversary can break a protocol key. And already that is a very tricky statement. When I say no adversary, that means there's some assumption about the set of adversaries, and nobody in this set can break the protocol. So the natural question is, well, what is this set? What are the adversaries that we're considering? When we say that if P and Q are secure, then the composition of P and Q is secure, it means we need some kind of notion of composition. So what is P, what is Q, what is the set of adversaries? And we're trying to answer these very general questions. So when we formalize this, you need some kind of language to express all this, and this language must have certain properties. And in particular, Julio told us about these superposition of causal orders, which are actually called non-causal orders. I'll explain in a minute why I'm using different terms. And that since this can be implemented, well, we want this included in our set, because if it's not there, then we can't make reasonable statements about what can be done, what an adversary can do. We also want causal orders to be dynamical, because we want in one time to be able to decide in what order things happen. And of course, you need a notion of composition just for the statement of P and Q. You can compose P and Q. So this talk is two parts. In the first part, I'm just trying to give you some motivation of what we expect from a theory of systems. So from some formalization of what is P, what is Q, what is an adversary. And then I'll give you one solution we came up with, which has all the properties we want. Now, in Julio's talk, he had these circuits which have some kind of classical ordering of the gates. And then he talked about indefinite causal orders or non-causal orders. I think he used the two words in a very similar way. And I'm going to actually distinguish. I'm going to split these indefinite causal orders into the ones that I call quantum and the ones that I call non-causal. And the quantum switch, to answer a question which I think was from Christian, I would say that we have a superposition of causal orders, but I wouldn't call it non-causal. And one of the reasons is that in this framework we have a hard-coded notion of time, and you can only go forwards in time, you can't go back, and yet we have a way of modeling the quantum switch. And these experiments which model them, which do the quantum switch, they also do it in this world without using any sort of weird quantum gravity or anything like that, in some lab where time goes forward, and yet they still manage to implement it. But of course, this is close to the question that Julio said about what does it mean to use a system once or twice, and you'll be able to judge for yourself if you think these implementations actually do that. So in my drawings, I have things like A and B, and there's a message going from A to B. So it's very different from the drawings that Julio had, because he had a notion of time going from left to right. I'm looking at more like A and B capital here are some kind of protocol, some kind of player. So you send a message, you receive a message, you send a message, and in most cases you can't actually just unravel it and write it as some circuit, because you don't really know in what order the operations are going to take place, because it might depend on the values of the input or something like that. Which is the notion of a dynamical causal order. When I draw something like this, it doesn't actually mean that first the message goes from A to B and then from B to A. The order might depend on when you receive the inputs from outside. You don't know necessarily when those come. The players might flip a coin and then choose to send a message. And the example of the quantum switch is exactly such a system. So in a very idealized way, we have this box, the quantum switch, which receives two inputs, like the control qubit and some state phi. And you want to either apply first U0 and then U1, or first U1 and U0 conditioned on the bit. So informally what you do is you look at your control bits, and if it's a 0, well, you're going to send your state to U0 and then to U1. If the control bit is a 1, you do it in the other way. So this is the dynamic decision of in which order you're going to do things. This sort of, so then U0 and U1 are applied in this superposition of two orders. And this is exactly a picture that Julio said he had, and then he removed for lack of time. This is one possible implementation which has been proposed, where we can think of the control system being, say, the polarization of a photon, and then the target system is in some extra degrees of freedom. But you need to plug something in the computer to use it. Maybe the other part. If the system that comes in says when it's polarized, say with a 0, it goes through the beam splitter, and polarized with 1, it gets reflected. If it starts with a 0, it goes, it enters here, it goes straight through the U0. It'll go on ground, it'll go on, and then the U1. And if it's the polarized with like the 1, so vertically instead of horizontally, it'll just get reflected. First go through U1, then it gets reflected, it goes around, reflected one more time. So it basically does it in the other order. So in this sense, we could argue that each system is used once, and you could imagine U0 and U1 to have some kind of counter inside, which is the laser pointer. Okay, thank you. I thought you could also change sides of that. Anyway, you could actually imagine that you have a counter inside which gets coherently implemented when a system goes through, and at the end the counter would each say 1. So you could kind of argue that you're using them once, or you could argue, well, the system had been lying around before and it didn't get used, it's still lying there, so you should count this as a resource being used. So maybe you should count it as twice, even if nothing goes in and our counter isn't implemented, it's still there, so it's consumed resources. So there are many different interpretations. So one thing we can do with the framework is basically model this kind of system. So more abstractly, this system which coherently says, okay, I'm going to send my system here, I'm going to send my system there, which actually can't be done in a straightforward manner just using circuits. So now, I also said we want to be able to compose protocols, and this is just some little example of how we actually use this the whole time when you write security proofs, even sometimes without knowing. Say we have some system, two parties, A and B, are interacting, and you write a paper and you prove that it's very close to some ideal system. Let's make them honest for simplicity and say it's some communication complexity where they have only a minimal number of states they can send, and our ideal system doesn't have this bound, and show that if you only have like two qubits of communication, you can still produce the right output within error epsilon, or something like this. Now someone might, so this is sort of implicit, you have an identity channel. And someone might say, okay, well, actually I don't have an identity channel, I have a noisy channel. Am I still able to do this? Because we just have a paper that proves this, and no one talks about what happens with the noisy channel. And then, well, the answer is yes, we actually know how to correct errors. So if, say, we know what the noise in our channel, we look at another paper which does quantum error correction. So you have a known noise model. What you do is your state, you encode it into a larger space, you go through here, there's some noise, you decode, and you get something which is going to be epsilon close to an ideal channel. So then we go back to our previous picture, and we're like, okay, we know how to correct here. So what we do is we do the encoding, goes to the channel, we do the decoding on the other side, and then we just run our same protocols A and B, and we want to argue that this is epsilon prime close to that. Now, in order to be able to for some small epsilon prime, to argue that this holds, there are actually a whole bunch of properties that we're going to need. We're first going to argue, well, this channel, we know that it has some kind of error delta, we're doing it twice, so we should have some kind of distance 2 delta between the two. But the distance actually that was proven in, say, this paper is just between these two things. So what is sort of has to hold, what we expect to hold is that if the distance between this part and this part is delta, and the distance between, well, this part and this part is also delta, then when you put them together, you get a distance of 2 delta, and when you go and add A and B around, this doesn't change the distance. But this is some property you expect of your systems, and if your systems don't have this property, you can't actually do this reasoning. And then you want to use the triangle inequality to say, okay, this has distance 2 delta, this has distance epsilon, so the sum of 2, so this distance should be 2 delta plus epsilon. So again, you need to prove that your theory of systems satisfies some kind of triangle inequality for this to hold. So what we really want is a set of systems, which are the systems we're going to study. So you could restrict them to classical systems if you want, or quantum systems, non-signaling systems, whatever you want. But it's very important to choose carefully what you're doing there, because all these security statements, they all have quantifiers in for all the ages, etc., which are very sensitive to the scope. And if you have some impossibility proof, for example, Julio said you can prove that you can't in a circuit do your quantum switch, what you're actually proving, you're not proving that it's impossible to do a quantum switch, you're proving that the language of circuit is not adequate to do a quantum switch. So you have to be careful about what statement you're making. And we want some kind of composition operation. I've been using it the whole time here. I've been taking systems, plugging them together, and what you actually need is that if you have two systems and you plug them together, you get a new valid system. And this is actually non-trivial. I'm going to give you an example in the next slide where this doesn't work if you're not careful. Now, we want this composition operation to be closed, meaning that if you take any two elements from our set, you plug them together, you get a new element in the set. And you also need some kind of sort of associativity of this composition, which I actually used in the reasoning here. At some point we had this system, so you can imagine brackets around here, and then we broke A prime into this, and then we put the brackets like this in order to argue that there's a distance. So you need to be able to move your brackets around with your composition operation to be able to run this kind of reasoning. And I also used a distance measure, so it just maps two systems to some value, which satisfies the triangle inequality, which satisfies some kind of notion of contractivity, which I also used to run the previous in the previous example. So these are things we expect from a theory of systems. And so I'm going to give you an example where the composition just doesn't work. And a very simple example, Alice and Bob each send a message to Charlie, and Charlie just outputs the name of the first, name of the player whose message he received first. So it's easy to describe Alice, it's easy to describe Bob, it's easy to describe Charlie using some kind of pseudocode. And Charlie receives the message. If he hasn't received anything, he receives something from Alice, he outputs Alice. If he had already received something from Bob, he doesn't output anything. So you can describe each system, but now when you put them together, and we're just saying, okay, what is this box? Is this system, is it going to output Alice or Bob? And well, the answer is we don't know. And you can of course discuss this and discuss why we don't know, but the explanation which I find to be the simplest is simply because I didn't have a complete description of my systems. I only had a partial description. I just said Alice sends Alice. I didn't tell you when she sent Alice. I didn't tell you how long it took the message to reach Charlie. And if, of course, you have an incomplete description of your systems, then you might not know what the composition is. But if you have a physical system, you actually implement this, you implement that, you plug that together, it's well defined what comes out. It's just, since we had this partial description, we weren't able to do it. So what we actually needed to get this closure on the composition is to model something which looks a lot like time. I'm just going to call it time for simplicity. It's a bit more abstract than that. So we model messages which are sent or received as a pair, which contains a value that you're sending, and some kind of tag, which you can think of it as some kind of time. Or here I'm calling it order information, just to try and be a bit more general, but it basically says when the message arrives. So if you do this in a quantum way, you'd have your value, which would be belongs to some Hilbert space, say finite dimensional, and our tag here, which we want t to possibly be infinite. So this is simply the Hilbert space created from an infinite set. So a basis of this space is given by the elements in here. So every element corresponds to a basis, and then you construct a Hilbert space with it. And it's just, this is the standard notation. So we're going to model all our messages as elements living in such a space. So for example, if I write the superposition of 0t and 1t, this is basically a superposition of the value 0 and the value 1 arriving in position t, or time t. And if I write this, a superposition of 0t and 0u, it's the message 0 has been received, or has been sent, and a superposition of positions of times t and u. Now, the only restriction we have on t, or the way, is that t has to be a set with a partial order, and it has to be countable. So we're doing it simply countable because we're doing a discrete computational model, so we just send and receive space, and everything we do is discrete. It has to be countable. And the partial order simply defines which message is before which message. Doesn't even have to be a total order, partial order is fine. But this partial order is essential because you can only, it's going to be a causal model, so you can only modify the future. Yes, you can't influence the past. So the order on t is going to define what messages can influence what messages. So possible sort of applications would be if we just want to think of t as being some kind of abstraction of time, you could take it to be the rational numbers. Or if you want to, you have a protocol which takes place in rounds, maybe t can be the integers, maybe that is sufficient. If you're doing a setting with some kind of adversary, you maybe want to use something like this, because what's nice with the rational numbers is between every 2 points there's another point. So an adversary can always behave faster and act between two rounds of honest players. And an adversary can always act before and can always act after, so there's no sort of restriction, there's no notion of beginning, there's no notion of next, so the next point in time is not defined if you choose T like that. One thing we're currently looking at is how to model relativistic protocols using such a model. So we simply think of T as a countable subset of R to the 4, which will model positions in space-time, and then the partial order simply defines 2 points are related if one is in the causal future of the other. Now, that was for the Hilbert space of one message, so something which looks like this. The protocol might decide not to produce a message, it might abort, or it might send multiple messages. So not only we can send no message, which I'm just going to model by a vacuum state, which like this, multiple messages, but we should also be able to send a superposition of 0 messages, or 1 message, or two messages. That's something we want to actually allow in our framework. So when I draw a system like this and put an arrow, the arrow basically corresponds to some Hilbert space which is constructed in this way. So we start off with this space of 1 message, and we take the symmetric subspace of n copies of it, and then we just do the direct sum over all n. So if n equals 0, we get a one-dimensional space, which is the vacuum state. And if n equals 1, well, we get this back. And if n equals 2, then we get 2 messages. And for n equals 3, we get 3 messages, etc. We just take the symmetric subspace because these messages are not ordered. It's just you receive, you can think of the classical case, you receive a set of 3 messages. There's no order in the set. In quantum case, you just do that with a symmetric subspace. So now what's actually a causal box? So what is sort of let's say the unit systems we consider? It's simply going to be a map from the input space to the output space. So suppose you have, here I just took 2 input y's and 2 output y's in this example. So it's going to be a map from density operators on this input space to density operators on that space. So since we have infinite dimensional spaces, I actually call these trace class operators. So this is just the density operators that would be the normalized ones. And the restriction is that this map must satisfy causality. Now, I'm not going to give you a definition of causality because it's rather messy, but the intuition is simply that an input time t can only depend on input which come before time t prime. So whatever comes after time t cannot influence something at t, so you just have to formalize that. So I'm going to give you an example to try and illustrate why a map from the input space to the output space is actually sufficient. So people who are familiar with Julian's work on quantum cones might be familiar with that, because cones do exactly the same thing. But it's a bit counterintuitive for someone who's not used to that. So just give you a very silly example. Suppose you want to compute the XOR of the 2 first bits that you receive. So you have a system that's going to receive bits, and it's going to wait, and when it has 2, it computes the XOR and it outputs the XOR. If you look at the standard computer science paper, they're going to probably give you some kind of pseudocode like this. They're going to say, well, the internal memory is initially empty, and then when you receive something, you do the following. If the memory is empty, you store the value. If the internal memory already has a value, you output the XOR of both, and you write in your memory that you're done. And if you're done, you do nothing. So you're going to output it at, say, the next time step. Now, you can actually equivalently represent such a system simply as a map from the input space to the output space. So if so we'd have to define how the map works on say, a basis of the space, but since this is classical, I'm just looking at all possible sets of possible inputs. So if you receive nothing, you output nothing. If you just receive 1 message, you output nothing. If you receive 2 messages, you output the XOR of the 2 at the time following the time at which you receive the second. If you receive 3 messages, again, you output the XOR of the 2 and you ignore the rest, etc. So this is actually completely equivalent to the other, except that I've completely skipped describing the internals of the system, which is actually makes lots of proofs much simpler and much nicer, because as soon as you start defining the internals, maybe someone in different work has used a different language, someone used Turing machines, someone used circuits, and then you have completely different ways of describing systems, and then it isn't quite clear what is compatible and what is not compatible, whereas you never really care about what happens inside. You only really care about the input-output behavior. That's the only thing which is relevant. So this is just a way of describing systems just through their input-output behavior. So now we come to the composition. What we want is this kind of composition operator, and the problem would be the following. I give you some map phi, which takes two inputs on y, which I'm labeling x and c, and produces outputs on y, b, and z. I'm taking some map psi, which has again two inputs and produces two outputs. I'm going to connect them like this, and I need to define what is the map resulting from the composition of the two. So to compose systems, we're going to do this in two goes. First, we're going to compose them in parallel. So parallel composition is first we do them in parallel, and once we have the two systems in parallel, we're going to put loops on the system. So these are the two operations we need to define, parallel composition and loops. So parallel, we get some kind of gamma prime, and then we put our loops on gamma prime, and then we're going to get the gamma we're interested in. So parallel composition is just trivial. Since these are two maps, the parallel composition of two maps is just the tensor product. The loops is the challenging one. So I'm first going to do it classically, because that's, I find much more intuitive. So suppose that you have a classical system. That means it's simply defined by a conditional probability distribution. So we have inputs on x and y and outputs on a and b. So we have this system phi, which is defined by this conditional probability distribution. And we want to compute what is the conditional probability distribution of psi, which is obtained by putting this loop. So now we only have this input and this output. And what we do is simply, everything which is output in A is input back into Y. So everything which is output in A is input back into Y, and you do the sum, and you get this. And this might be very weird, like why on earth would this be a valid probability distribution? And in general, if you just plug in any valid distribution here, you can get complete and utter nonsense here. However, if your distribution here satisfies causality, then you're always going to get a normalized distribution which also satisfies causality. So here, really, the causality notion is actually essential. If not, the composition is not well defined. If we have a more general system, it's like the non-causal systems that can actually be captured by Julio's work. As far as I know, there's no generic way of composing systems. We just don't know how to do that. So now, in the quantum case, we're also going to use the TYQI2016 isomorphism, but I'm going to give you a slightly different formulation of it. The one you're probably most familiar with is something like this. It's some kind of operator which is defined in this way. So it's the TYQI2016 representation of this CPTP map gamma. This is rather inconvenient to use in infinite dimensional case because this is actually an unbounded operator. So we're going to instead define a successive linear form. So it's basically a scalar product, something which is linear in one argument and anti-linear in the other, which is defined like this. You can think of it as taking this form and then just hitting it on each side with the kep and the bra of these states. So it basically gives you, it's a map from two vectors to a complex number. And given this representation of the map, we can define the loop in exactly the same way as the classical case. We just generalize it like this. So you have this linear form which is defined for your system, which takes two inputs, x and y, a and b. So inputs x and y and outputs a and b. And everything which is output on a, you input it back into y. So everything which is output on a, you input back into y. You just have to take a complement here for the signs to work. So you basically pick any basis of the Hilbert spaces. Of course, a and y have to be isomorphic for this to even make sense. And then you just do the sum, and you're going to get a linear form for the map after putting the loop. And the last thing we need is some notion of distance, which satisfies all these properties of triangle inequality and contractility, etc. So here we're actually going to do it a way which is very standard in cryptography. We're going to use distinguishers to define a distance. So formally, a distinguisher will actually just be another causal box. So the idea is you want to distinguish between phi and psi, so you're just going to plug some distinguisher in which can interact with it, can put an input, read the output, put another input, read the other output. And at some point it has to take a decision. Put output 0 or 1 saying, oh, I'm interacting with phi or I'm interacting with psi. So if I just use this notation to talk about the output, which is going to be a random variable, the distance between the two systems is simply defined as the statistical distance between the outputs. And then you take the supremum of all possible d's to actually get a notion which, to get the distinguishability between the two. So it's easy to kind of see that this satisfies the triangle inequality because the statistical distance satisfies the triangle inequality. And it also satisfies contractivity because any other system that you might sort of plug in here and plug in there could actually be included in the distinguisher. So, in summary, what we have done so far is developed a framework which allows us to capture all these systems that we want. So we have a dynamical structure, we have superpositions of causal orders, we have some kind of notion of time. And current things we're working on is some cryptographic applications. So we're looking into relativistic protocols, and in particular, how can we have composable definitions for relativistic protocols. And we're also working on a non-deterministic model of systems where time is unknown. So here are all my systems, they all have this time parameter, but in reality you maybe don't know how your system is going to work. So we can actually think of that as a non-deterministic system where there is underlying it some kind of behavior which depends on time, you just don't know what it is. So your system would be described by a set of all possible behaviors, and maybe the dishonest players know how your systems behave, but the honest players don't know. It isn't really clear how to define complexity in such a framework, like the standard notion of taking classical complexity count gates. Doesn't seem to make much sense because now you might have a gate which is in the superposition of being used or not, so that doesn't, you maybe need more physical properties like energy or time, which is actually well defined in this case. And we're also trying to understand better the relation to these non-causal models, exactly what is included in this model and what is not included. And one of the reasons we were doing all this is it's actually a component of the abstract cryptography framework, which is some cryptography framework being developed by Maurer and Henner to model cryptography. And the framework is done in such a way that it's extremely modular. The little parts of the framework, you just have some kind of abstract description of them. So for our case, what we really need is this desiderata that I put on the slide at the beginning. We want systems to behave in this way. And if you have systems to behave in this way, you can plug them in the framework and you can start making statements about them. So we came up with one solution which has all the systems we want and behave in this way, but you could actually plug in anything which satisfies this sort of set of axioms. You can actually plug in a framework and do interesting stuff with it. So the non-deterministic model model systems we're working on should also satisfy this, and then you could plug it in, and you can maybe simplify it by looking at, say, only classical systems and whatever variations you want.
Question. Is there a question in the front?
So just to see if I understood, just to see if I understood correctly, a little bit, like to contrast with the thing I was saying. So when you're saying some maps like the switch can be realized actually, but they are not in the language of quantum circuits. This is what you said at some point, no? So what you do here is to enrich the language of quantum circuits by adding a time label to all the systems. No?
Yes.
So the system is a time T0, T1, T3, and so you allow, with this language, you can describe situations when you put a system in the superposition of being a time T0 or a time or a later time T1, right? So this would allow you to describe situations like the switch within the language.
Yes.
One thing, however, so this is a good as a descriptive tool. On the other hand, this framework doesn't tell you what are the possible ways to connect or the possible evolutions that you can build in general, no? Because whether or not you can connect to channels or to networks in a way will depend on what things you are connecting. No? So we cannot apply the switch to every bipartite channel, but only to pairs of channels. So there will be issues like we can describe all these situations, but what are all the situations that we can describe?
Okay, so we don't really have that problem here. I had this picture where I had the quantum switch and I had two boxes, U0 and U1 below. So we can describe the quantum switch in the language of this framework, and then you can just plug, you don't have to put two boxes, U0 and U1. It doesn't have to be a bipartite system. You can actually plug any system in, and composition is always well defined.
no, maybe I meant something slightly different. So that, so I mean, if we have these two boxes, for instance, there is a memory going from one box to the other.
Between U0 and U1?
Yes.
Yes.
So in that case, in general, we would get absurd results if we apply the control switch.
In your framework, yes. In this one, no. You always get something reasonable.
I doubt that.
The whole point is that the framework is closed down at composition. Take any two systems, plug them together, you're going to get something which is included, which is an invalid system.
We cannot just transform a channel with memory into the switch of these two things just because there is the memory. So understand that for some channels you can do this, but maybe there is we mean different things here, but for sure in our sense we cannot do this for every possible channel.
Yes, and I think that's maybe one of really the differences. When you said before this implementation of the quantum switch and the way we model the quantum switch, are we really doing the same quantum switch in the same way as you're doing it? You could argue, say, no, we actually have 4 systems, not 2. We have U0 at time 1 and U0 at time 2, and we have U1 at time 1 and U1 at time 2. So you could argue that we're doing actually different things.
So it would be really 2 uses.
Yes, again, it depends how you count uses. Put a counter in which you only increment coherently when you receive the state, and the count only increases by 1. But
yes,
the box is always there. And
yes.
it's there time 1, it's there time 2.
Yeah. I see.
Maybe in the interest of time, we move on to the next. Is there next? That's time, Christopher, again.